Hello, class. In this session, I'm going to demonstrate some MATLAB code for you to draw a sine wave. So here we can always start from a new script. Right now, I suggest that for you to begin with, you use this live scripts so it can produce results you can see right here in the next section. So when we do this, we first can do clear all, close all, and the CLC. So these will clear out the workspace, close all the figures. For example, I have a figure 1. Then I want to plot a point, say 0, 1, and then 9, 2. Okay, so this figure will pop up. So when we use close all, the figure will be renewed. And then you can also see there's workspace here. If you want to start a new script, you don't want to mess up with these variables already been loaded into the workspace, you can use clear all, and then it will be cleared. So if I want to have a clean command window, I put CLC here, and then it will remove all the previous materials here. So usually what I can do before this is I can put in a text session, say, here, this is the first demo code for ECP 451, 2022, okay? So the purpose for that is plot sine, plot the voltage, waveforms, and show Rms value, show phase shifts, okay? So once we start to do that, we can clear it out for a new session. So we can set up it here. For example, we can do this. We just copy it in. From here, see. So now I have, this is my frequency. And then this is 2 pi times frequency is my omega. And this is for one cycle. So when you plot a sine wave, so one cycle of it, this is one cycle. So the frequency for this is in 1 second, you will have 60 such curves, okay? And then for each cycle, this is a complete cycle. If this is a cosine wave, you can have this as a complete cycle, okay? So that complete cycle will be 1/60. So that's about 0.0167. So it's about 16.7 millisecond, okay? So we're just going to show that. Okay. Now let's see if we run this selection. You can see this is 60 hertz. My omega equals to this. And the one cycle equals to 0.0167. Okay, so this just show the initial setting of my waveform. And then when I want to do the plot, the first thing I need to do is to set up delta t. So what is delta t? The delta t basically is this. So I want to plot out how long, right? So this is 1 divided by f times 3, so that would be, if that's the case, I'm going to do 3 cycles, 1 and 2 and 3. So each one, like if it's a cosine wave, is like this. Let me see here. It will be something like these. So this will be 3 cycles. So if a cosine wave, it will be 3 cycles. Okay, I'm not really good at drawing those things. But later on, you can see that. So because it's 3 cycles, so one cycle is this long, right? So if we times that by 3, so that's 3 cycles. So this defines how long this plot would be, and then delta t will be the interval of it, right? So what I want is this is the step size. So in each cycle, I want to have 100 pointed calculated, okay? And then this t basically is a vector. It contains all the time points in between this is my total one, okay? And then this is my delta t, okay? So this t contains all these points in here, okay? So that's these points. There will be a number of these points in here, okay? So let's see if we run that. You will see that the t altogether have 301 point inside this t vector, okay? So if we want to make it this is a row vector. So it's one row and 301 columns. But if I put a prime here, then when I run it, you can see that this basically rotates its direction. So now this t is a vector with the 301 row, and then it's only one column now, okay? And then next, I'm going to set up my voltage values. You can see here. So the RMS value is 120. So this is my household, right? So if we have we plug in to the wall, then this is voltage level in our house. So our sine wave is not the RMS value. So the magnitude of it, the instantaneous the maximum value of it, you need to use RMS value times square root of 2, okay? And then usually we use a cosine representation, and then this is omega t plus 0. This is the angle. So the angle is in radians. So if we want this to be in degree, what we would do, we can do this. We can say cosine d instead of that, and this would be in degree. So what's the difference that will make? If I want to say, hey, initially my angle is 30 degrees, so you can directly put 30 here, okay? So that way, let me just plot it out so we can see the difference, the figure. Let me just copy this out. So this way I'll plot, this is my axis is x, you can see this value here. And then my y-axis is VA, okay? So if I run this, you can see that here is only from 0 to 0.05. So that means my length of t here is VA, that means t is too small. So my VA is like that. Let me just T delta T. Okay. So the reason that I should do this is because when I times the value, I have I run all the code, and then you can see that for the sine wave here, this is a 1 cycle, this is 2 cycle, and this is 3 cycle, okay? And then this total length of time is 0.05. So what if I change this value to be a little bit shorter? Let me see here. Let me see if we have only 10 points, what will happen? I run that again. And then you can see that because I only have 10 points, there's not enough points. So they have to connect these 2 points together. So it doesn't look like a sine wave anymore. So if I have 100 here instead, I can run section. You can see this will be much more smoother, right? So if I want to see the effect more clearly, I can use hold on. So that way, when I do this, I can see the differences, because when I use hold on, they won't eliminate the previous plot that I have. So if I run this, say I only have 5 points, I run the selection, you see like that, and then let me change that to say 10, and run that. You can see that this is the difference when we select a different number of points to draw this curve. Say if I have 100, then we can run it. It'll be even more smoother, okay? So what if I want to get rid of this, because I want to see start from a clean plot, then I'll just run the whole thing. And then because this is a close all, it will close the previous plots here, okay? So this is how we select a different resolution to plot this curve. So the other thing we can change is this cycle. So if I say 10 cycles, then when I run it, let's say run. So now you can see it's much longer. This is no longer 0.5. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So it has 10 cycles. So the other thing we can play around with is the angle here. So suppose I want this to be, say, 30 degree. So I need to put down here as cosine D, okay? Because it's a degree. The alternative is I can use pi divided by 6. But if I use pi divided by 6, it's in radius, so I need to get rid of this D. So either way will be okay. So now let's make them blue, and then make this a dot. So let me run that again. So you can see that if I don't want to do this, I want to make them shorter so I can see it more clearly. So I'm just going to eliminate that. So you can see this is how the 30 degree is. So if this is a minus, then let's make it red. Then we run this section. You will see that if it's a minus, it will be plus is leading, minus is lagging. So if I change this to 0, what it would be? It should be right in the middle of these two. Let's see if that would be the case. So let's make it a solid line. And then now we can just run selection. So you can see it's right in the middle. So now you can see that if this angle is plus, then that means it's leading. So it's leading this 0. When it is 0, if this is plus 30, it will be leading, and the minus 30, it will be lagging. Okay. So next, what is the RMS value? So if we want to produce the RMS value, so that would be the equivalent to DC voltage. So that would be equals to the magnitude-wise, that would be that. But if we want to plot a curve, we need to have the same length as t. So I can do one of these things. So we can use this to times times once. So once is what? Once will produce this. So 1, and then once with like 1 row, and then how many columns? This is the length of t. So the length of t is what? The length of t here is this much. So it's 301, okay? But one thing we need to notice is because this t right now is 301 times 1, so it's 300 rows and then only 1 column. So we need to have the same dimension. So that means here, if I really want to do that, I need to do length t and 1, okay? So that way I can produce a voltage and then that will be the same value for the entire period of time. So I can hold on that. I can plot, let's see, plot another curve. This is VDC. I want to make it, say, magenta or just green. Yeah, I haven't used green yet. So let's say run it. So you can see this is the RMS value of it. You can see the RMS value is the equivalent DC value of the sine wave. That means the energy that I consumed in a cycle here, like say here, this is the energy I consumed. If I use this AC voltage, it will be equivalent to this part, okay? Okay, so that means that at this half a cycle, this time, if I use a DC to supply the same resistance, it should give me the, it should consume the same amount of energy as this AC voltage would let my resistor consume. So these two, the area-wise, they're equivalent. So in our next demonstration, I'm going to show you how that can be demonstrated by using MATLAB code. Thank you for watching.